Alright, topic of this video is dilutions. Dilutions is something that's very, very important in all of chemistry. If you work in the lab, it won't be long before you need to perform a dilution. Consequently, we need to know what we're talking about when we refer to dilutions, how this works, and we're going to get a little bit quantitative. Alright? I'd rate this an importance of 4 out of 4 stars. It's a pretty vital skill for any lab scientist, okay? So to start this discussion, I'll ask this question. If you go into a lab and you find a reagent on the shelf, okay, let's say it's got a molecular weight approximately 100 grams per mole. Could you take that bottle, say it's a powder, and prepare 1 liter of a 5 nanomolar solution directly? Well, if it's 5 nanomoles per liter, and you want 1 liter of it, that means this process is going to require 5 times 10 to the minus 9 moles. You need to have that number of moles, 5 times 10 to the minus 9, dissolved in this 1 liter volume to make this work. Now, if your formula mass is 100 grams per mole, and you need this many moles, you would just simply multiply them together and get the mass. Now, clearly that would move the decimal place, what, 1, 2 spots? So you'd have 5 times 10 to the minus 7 grams, something like that. You're going to be able to weigh that out? I don't think so. That's not going to work out so well. Even the best balances that your lab's going to have, you get down to a milligram and you're sort of strained for accuracy. And a milligram, of course, is many orders of magnitude larger than what you would need here. Right? You need like 10,000 times less. So this isn't going to go so well. So what we need to do instead of making a direct preparation is we need to perform a dilution. What our strategy would be in this case is to go into the lab, maybe get ourselves, I'm going to draw a beaker here. You'd probably use a volumetric flask, okay? And in this process we'd make a stock solution. Stock solution is going to be more concentrated than what we need. Okay, maybe we'd make a 10 millimolar solution or a 1 millimolar solution, something like that. But it's much more concentrated than what we need for our experiment. Okay, this is what our experiment requires. After we make our stock solution, we can then dilute this down with additional solvent. The way that that works is then we would take our stock solution, get ourselves another volumetric flask, and again, usually use volumetric flasks for making these solutions. You take a fixed quantity of our stock solution, pipette it into the flask, so that's in the bottom of the flask, and then you'd go and you'd add more solvent. You'd add solvent until you dilute it to the mark. And if you add just the right quantity of stock solution into the specified total volume of the flask, you're going to be able to achieve a concentration that you desire. Of course, the trick to all this is figuring out how much of the stock solution do you need to add to make a given volume of solution, the diluted solution. Okay, so we call this process making a dilution. We take a more concentrated solution and dilute it down to be a lower concentration by adding additional solvent. That's what we refer to when we talk about dilutions. Now, the equation down here on the bottom of this slide, I'm going to highlight in red. This is known as the dilution equation. It's used all the time for making dilutions. You should be familiar with this equation. You're going to use it often if you ever work in the laboratory, okay? All this is a statement of the conservation of mass, basically, okay? Whenever you multiply a molarity, which is our concentration times a volume, it gives you a moles. So on the left, I'm computing the moles of stock used, or really not necessarily the moles of the stock solution, that's probably bad terminology, but the moles of the solute in the stock solution is really what I'm computing over here. And on the right I have another M and a V term. This is the molarity of my diluted solution, the volume of my diluted solution. That tells me the moles of solute in diluted solution. So here's the deal. All this equation says, it's really quite simple, is the moles of the solute you transfer out of the stock solution and you put in this flask is equal to the moles of the material in the flask. So, duh, right? That makes perfect sense. That's no surprise to anybody. But the equation, as it's written, is very, very useful for keeping track of this quantitatively. So let's see a sample problem that you might encounter. Now, are you going to see an equation that deals directly with dilutions on your semester exam or your final exam? Maybe not, okay? But in my experience, the test writers, the authors, they are very wise people and they're very good at writing questions. So what they tend to do is to couple multiple concepts into the same question. You have to know multiple things to get the correct answer and be confident in your result. And this is one of the things that they can throw in, and they can and do throw in. You're expected to understand this whole dilution equation bit. Another thing I see about this dilution equation from time to time, people like to use it when dealing with titration stoichiometry, because of course molarity times volume is moles, and that can relate, moles of one substance to the other. And that might work if it's a one-to-one stoichiometry, but if the stoichiometry of the reaction is not one-to-one, it's not going to work. So I don't encourage you to use this direct equation for titration stoichiometry computations, okay? Because if you're not thinking about it, it's easy to make a mistake. But let's see what we do use it for. Look at our sample problem. How many milliliters of a 2 molar HCl solution is required to prepare 1 liter of a 0.15 molar HCl solution? Okay, so let's review what we got here. We got a stock solution. It's the more concentrated solution. It's in our beaker here. This is my beaker with the stock solution. Bear with me, I'm not an artist, okay? I know from the problem that it's 2 molar in HCl, aqueous, 2 moles per liter. I've got some volume of it, and it will say enough to get the job done, okay? And I want to take that 2 molar HCl, grab a nice 1 liter volumetric flask off the shelf in the lab. So we get ourselves a nice vol flask. A nice big 1 liter vol flask. I want to be careful with that, don't want to break it because it's expensive. The molarity of this solution needs to be 0.150 mole per liter. This is my diluted solution. Stock, more concentrated, diluted solution, less concentrated. Okay, so let's return to our dilution equation and then work the math for this real fast. I've got M1V1 equals M2V2, or M's are the molarities, V's are the volumes. Sometimes you see M stock, V stock, M dilution, V dilution. If you want to use that form of the equation, that's fine. I just reduced it to numbers, but of course what we're talking about with 1s and 2s here are different solutions, whether it be the diluted solution or the stock solution, okay? So I'll pretend that the stock is my 1s here, okay? So my stock solution is 2 molar, and I need some volume of it, V1. I don't know what V is yet. That's going to be my unknown quantity here. However, I know that I want to prepare a diluted solution, which is solution number 2. That is 0.15 moles per liter. And I want to have, when I'm all said and done, 1 liter of this, okay? So if I do the math over here, of course this is the concentration, so that's in moles per liter. So liters cancel and I'm left with moles. And what this computation tells me is that when I'm done making this solution in this volumetric flask, it's going to contain 0.15 moles of my HCl. That's how many moles it's got to be in there to make this work. Now how am I going to get that? Well, I'm going to transfer some stock solution in. How much do I need? Well, I can write the algebraic expression 2v1 is equal to this. And solving for v1, I can solve for that using a calculator real fast, and I find the answer is 0.075 liters. That's how many liters I need to answer the question. I have to multiply that by 1,000, which yields the realization that I need 75 milliliters of my stock solution to make this work. So what I'm going to do is I'm going to get myself a pipette that's capable of a 75 milliliter volume, and I'm going to pipette 75 milliliters into the bottom of this empty volumetric flask. I will then dilute to the mark, and I will have the appropriate solution. Hope you've enjoyed this video on dilutions. It is a very important concept, and you should know it before you take your exams.